All right, let's talk about 2.7. This is linear and absolute value inequalities. So now you are working with what a lot of elementary school teachers call gator notation, right? The alligator eats the bigger number. So you're looking into things like, is it greater than this? Is it less than that? Is it between these two numbers? So those kinds of scenarios where now it's no longer equal signs. Now we're looking at inequalities. Your answer to all of these is an interval, not a number. And in order to kind of simplify our lives and make everything really standard and uniform across all math classes, we use interval notation to do this. You have two parts. You need to pick the numbers that are the bounds of the interval. And in this scenario, you have an example here, 3 to 0, or 3 to infinity. These are your bounds of the interval. This means the interval starts at 3 and goes to infinity. Now the parentheses and the style of parentheses around them also has a meaning. So if I use round parentheses, like I have on this side, this means it does not include. And does not include would be if I was using greater than or less than. Okay, so it doesn't have the underline. If it has the underline and I do want to include the interval, we use square brackets. And you can use them separately. Okay, so what is on the left side and what is on the right side, they don't have to match. There's no particular order, there's no particular reason for them to be the same all the time. It's not, this isn't grammar, this is not an English class, right? We're using the same symbols, but we're using them in a math setting. And so they don't have to match. In this case, a square bracket just means include the number that it's next to. A round bracket means don't. Okay. We also use things like set builder notation, and this is a little less common in algebra, a little more common in statistics, which is why we're going to kind of talk about it and brush over the top of it a little bit. Set builder notation, when I read this out loud, this is set builder notation, has to have this curly braces around it. When we read this out loud, we are saying the set. Okay, so curly braces indicates that I have a set of things or a collection of objects, a group of whatever. Okay, a group of things, which we usually use the variable x. You don't have to use x, it will be a variable there. And this vertical line stands for the word such that. So I have a group of things such that these things are between -2 and +6, including -2, but not including +6. Okay, and with numbers, it doesn't really make anything shorter in terms of numbers unless I'm doing something like I'm taking the set of things such that x is an even number. So now I'm working with the set of all the even numbers, and I don't have to go through and list every single even number. I just say I want the even numbers. If I'm picking from categories, I want to say take all the things from the categories such that the thing is blue. Okay, so set builder notation has a lot more application in qualitative type of data rather than quantitative. So quantitative is if I'm working with actual numbers themselves. Qualitative means I'm working with the qualities of something. It's green, it's blue, it has brown eyes, it's male, it's female, it's, drives a truck, drives a car. Those are qualities, so things I can't really define. So we use set builder notation in algebra because it's a good place to kind of cross over. But more often than not, when you actually use it in problems, it will be in a statistics scenario rather than solving inequalities. Okay, but it is in here because part of the goal of this class is to get you ready for stats. So it's here. You're welcome. Use it, practice it, get into it a little bit. Okay, solving inequalities. The basic ideas don't change that much from when we solve things with equal signs. The biggest difference is if I divide or multiply by a negative number, and it doesn't matter if it's on the left or the right, doesn't matter if it's a whole number or a fraction. All that is important is if I am dividing or multiplying by a negative value, I need to turn the inequality around. If you are adding or subtracting, the inequality stays, just doesn't change. There's no reason to look into it a little further. If I am multiplying or dividing by a negative number, I need to flip my inequality. Otherwise, everything else that you're doing in these problems is exactly the same as what we would be doing in an equality. Okay, so the rest of these slides are just examples, and I will do some of these and then probably like erase a little bit and go back in. So if you haven't finished copying the problem down by the time I'm done talking about it, remember this is a recording. Just hit pause. You can even just watch what's going on and then pause and screenshot it into your notes. It is a recording, so take advantage of that fact while you're working through this, okay? So x minus 15 is less than 4. So we treat it like that's an equal sign, so we're going to add 15 to each side. So x is less than 19. Now, if I was working in this notation, I would say, okay, less than 19, so open dot at 19, I want less than, so I'm shading to the left. But we want to now start working in interval notation. And interval notation always goes from the smaller end to the larger end, which means I'm going to start at negative infinity and work my way up to 19. We never include infinity, so infinity will always have a round parenthesis. And in this case, 19 has an open dot and it's not underlined, which means I use a round parenthesis for that. So my answer to this in interval notation would be from negative infinity to positive 19, not including either end of that interval. Okay, 6 is greater than or equal to x minus 1. We're going to add 1 to each side. So 7 is greater than or equal to x, or if it's easier to read, x is less than or equal to 7. Okay, if you decide to flip it around, make sure that your alligator is still eating the larger thing. So if it's eating 7 in the top line, it should be eating the 7 in the bottom line. Okay, less than or equal to 7 means that I have a closed dot at 7. I'm still shading off to the left. And in interval notation, I'm going to go from negative infinity to positive 7. But this time, because I colored in the dot, I use a square bracket to box in the 7. Five minus x is greater than or equal to 10. I'm going to subtract 5 from each side. So negative x is greater than or equal to 5. Then I have to divide by a negative 1. So I have a positive x, I have a negative 5, but because I divided by a negative value, this inequality now becomes less than or equal to rather than greater than or equal to. So same inequality, it doesn't change the equal to part, it just turns it around. So now I am less than or equal to a negative 5, and my interval goes from negative infinity to negative 5, including the negative 5. Okay. The last one on this page, I've got 4x plus 7 is less than or equal to 2x minus 3. You can solve this in whatever order you prefer, but the same idea as equalities apply. I want x's on one side, numbers on the other. So let's subtract 2x from each side. So 4 minus 2x is 2x, plus 7 is less than or equal to negative 3. Subtract 7 from each side. So 2x is less than or equal to negative 10. Divide by 2, so x is less than or equal to negative 5. Okay, common question that I get there. I do not flip the inequality. I divided a negative number. The 10 was negative to start with, but because the number I'm dividing by a positive 2. Because that's positive, the inequality stays where it is. I don't have to turn it back around. At this point, try the next two. Pause the video, try the next two, see if you can get them. Make sure you're on the right track, make sure you're kind of understanding what's going on. The only way to understand math problems is to practice them. So pause the video, practice them, and then come back and we'll talk through it. Okay. 13 minus 7x is greater than 10x minus 4. So I'm going to add 7x to each side. So 13 is greater than 17x minus 4. Add the 4 to each side. So 17 is less than 17x, which means that x is less than 1. So my interval goes from negative infinity to positive 1, not including the 1. Right? I need to be less than 1, which means the smallest number allowed is negative infinity, and the smallest number always goes on the left. Negative x plus 4 is less than 1/2 x plus 1. So let's just subtract half an x from each side. So negative 1 minus 1/2 is negative 3/2 is less than 1. Subtract 4 from each side. So negative 3/2 x is less than negative 3. Multiply both sides by 2 to cancel those out. So negative 3x is less than negative 6. And then divide by negative 3. Cancels on the left, so x is greater than positive 2. I'm dividing by a negative number, so I turn the inequality around. So that interval is going to be from 2 to positive infinity, because now I'm greater than 2. So the biggest number allowed is in positive infinity, which means the bigger number goes on the right. Okay. 3/4 x is greater than or equal to negative 5/8 plus 2/3 x. Now, I don't really want to mess with the fractions, and because I can treat it like an equality most of the time, I'm going to just kill them. I'm going to get rid of them. So a common denominator for these three numbers would be 24. So I'm just going to take every single term and multiply it by 24. So I have 3/4 x times 24 is greater than or equal to negative 5/8 times 24 plus 2/3 x times 24. So 4 goes into 24 and leaves behind a 6. So 6 times 3 is 18x. 8 goes into 24 and leaves a 3. So negative 5 times 3 is a negative 15. 3 goes into 24 and leaves an 8. So 2 times 8 gives me 16x. And now the fractions are gone and I can just solve it however I want to solve it. So subtract 16x from each side. So 2x is greater than or equal to negative 15. Divide by 2. So x is greater than or equal to negative 15/2, which means my interval starts at negative 15/2 and includes it, right, or equal to, so I've got a square bracket, and keeps going up to positive infinity. Gets larger, so it goes towards positive infinity. All right, the next one is an example of what's called simultaneous equations. And I probably have a better example on the next slide, but they're out of order apparently, so here we are. So simultaneous equations means I've got a variable in all three parts. And sometimes I can just solve it as written, and sometimes I can't. And this is a scenario where I can't. Okay, what we have to do here is we're going to take the left two and solve those. And then we're going to take the two on the right and solve those. And we might have more than one answer here, and that's totally fine. Not a big deal. We end up with more than one answer. We put them back together. So let's solve the left side. I'm going to subtract x. So 3 is greater than 6x plus 2. Subtract 2 from each side. So 6x is less than 1. Divide by 6. So x is less than 1/6. Okay, that means I've got the interval from negative infinity to positive 1/6, not including 1/6. And then I'm going to look at the ones on the right. So subtract 5x from each side. So 2x plus 2 is greater than or equal to negative 10. Subtract 2 from each side. So 2x is greater than or equal to negative 12. Divide by 2. So x is greater than or equal to negative 6. And that interval is going to go from negative 6 up to positive infinity. Now, the tricky part here is putting those back together. When we do these simultaneous intervals, they get joined by the word and. And what that means is when I get down to the bottom here, I'm going to draw these intervals. So if I go from negative infinity to positive 1/6, I've got an open dot and I'm shading out to the left. If I go from negative 6 to infinity, I have a closed dot and we're shading to the right. And because this is an and, I only care about the part of all of that where I have both things, okay, where both of those lines are shaded. So I don't care about this one happening out here on the right. I don't care about that part happening out on the left. My final answer is going to be negative 6 to positive 1/6, including negative 6, open parenthesis on 1/6. Okay. This last example over here, use absolute value notation to describe all numbers a distance of 5 from number 7. So absolute value notation is actually pretty straightforward. You're going to have a basic pattern. You're going to have x minus your goal, and that has to be within your tolerance. And the only thing that's going to change here is you might change the equal sign to less than or equal to, greater than or equal to, less than or greater than, depending on how these are worded. And so the tricky part of these is you have to read them really carefully. Okay, if I want to know a distance of, they want exact. This is telling me find exactly the right thing. And they just want me to use notation. So I've got x minus, my goal is to be at the number 7. My distance away from that, which is called your tolerance, is 5. And because they want notation, I don't have to solve it. That's it. That's your answer. That's what they want. They just want you to say, this is how I would do that in an equation. You do not solve it. Don't have to solve it. There's nothing to solve. That is what you would type in as your final answer. what happens if I am solving with absolute values? So we know from the last section that when I work with absolute values, I have to work with two cases. And when I work with absolute values here, I still have to kind of consider that scenario, but things are going to look just a little tiny bit different. Okay, so let's say the absolute value of x plus 9 is greater than or equal to negative 6. Now, if I'm paying attention, remember, the point of absolute value bars is to make things positive, which means it's making it greater than 0. So whatever I plug in there, the absolute value bar is going to make it bigger than 0, which means it's always going to be bigger than negative 6. So I don't have to do any algebra here. The absolute value is by itself. The number on the other side is negative. So that means this is going to be always true. And since it's always true, it doesn't matter what x value I plug in. And so we would say you can use all real numbers. The problem is that's a lot of writing for mathematicians. And so in interval notation, instead of saying all real numbers, we say you can use anything from negative infinity to positive infinity. Okay, that's the interval notation version of this is always true, or you can use any real number. It's negative infinity to positive infinity. Okay. The absolute value of negative 2x plus 7 is less than 13. Okay, so the absolute value is by itself. It's less than a positive number, which is totally allowable, but it's not always going to be true. Okay, so it's not a scenario where I'm going to be greater than a negative number, which is always true. This might happen. Okay, so I've got the absolute value by itself. I'm still going to split it into two cases. So I'm going to take negative 2x plus 7 and negative 2x plus 7. On one of the cases, I'm going to keep it as written. So it's going to be less than 13. Now when we did inequality or equalities, we would make this a negative 13. And we're still going to do that. The only other difference is I'm going to flip this sign around. So I'm going to be less than 13, but also greater than negative 13. And then I just solve these. So negative 2x is less than 6, divide by negative 2. So x is greater than negative 3. On the right side, negative 2x is greater than negative 20. Divide by your negative 2. So x is less than positive 10. Now this is less than, and less than translates to an and. So I need to draw my number line and figure out where I'm going. So I need to be greater than negative 3. So open dot, shaded to the right, less than positive 10, open dot, shaded to the left. The only places where these would overlap is between the 3 and the 10. So my final answer is the interval from negative 3 to positive 10. And that's an interval, not a coordinate. All right, negative 2 times the absolute value of x minus 4 is less than or equal to negative 6. Now, the number one mistake on this particular problem is that we see that we are less than or equal to a negative number, and we say, oh yeah, I can't do that problem. That doesn't exist. No problem, not going to work. Well, the problem with that thought process is I have this negative 2 here, so I can't decide whether or not it's going to work until I get the absolute value by itself. And until it's by itself, don't make any decisions about it. So the first thing I need to do here is actually divide by -2. Now remember, I'm dividing this because I cannot distribute in. I am not allowed to do that. Okay, I cannot multiply that -2 into the absolute value. I have to just divide it away and leave it alone. Okay, so this absolute value of x minus 4 is now greater than or equal to a +3, which is possible. So now I have to solve it in my two cases. So the first case is as it's written. The second case, I'm gonna turn the inequality around and change the sign. Now with less than, with greater than is an or scenario. And I will show you what that means when we get to the end of this. Less than is an and, greater than is an or. So we'll go back and we'll finish solving these. So add 4 to both sides. So x is greater than or equal to 7. Add 4 to both sides here. X is less than or equal to 1. When I graph that, greater than or equal to 7 is a closed dot shaded to the right. Less than or equal to 1 is a closed dot shaded to the left. If this was an and, okay, it's not an and, but if it was an and, I don't have anywhere where they overlap. But because it's an or, I'm just going to take anywhere that's shaded. So I'm shaded in this spot, which goes from -infinity to 1. I'm shaded over here on the right, which goes from 7 to +infinity. And to say that I have to keep those together to keep that and idea involved, we use what's called a cup. And my pen's not drawing. Okay, looks like a capital U. It's not a capital U, but it looks like one. It's a union symbol and is sometimes called a cup. I don't know, just is what it is. Okay, so it's a union symbol that means or. Okay. And it just means there's multiple places on the number line where you could go and get answers. We're just going to use this one. Okay. Given the equation, y equals -1/2 times the absolute value of 4x minus 5 plus 3. Determine the x values for which the y values are negative. So it's saying, figure out what I have to put in to get an answer that is negative. And all of my negative numbers are less than 0. 0 is not considered positive or negative for our applications. Okay, we're just going negative, which means don't include 0. I just want to be less than 0. So what this is asking you to do is say that -1/2, the absolute value of 4x minus 5 plus 3 is less than 0. So -1/2 times the absolute value of 4x minus 5 is less than -3, multiplied by a -2 to cancel this out. So the absolute value of 4x minus 5 is less than +6. Then we split our cases. So 4x minus 5 is less than 6, and 4x minus 5 is greater than -6. So 4x is less than 11, which means x is less than 11/4. 4x is greater than a -1, which means x is greater than -1/4. This is less than, which means I'm looking at and. So my interval is going to go from -1/4 to +11/4. And yeah, I didn't draw the step with the number line, you can draw that. Draw it out, make sure that you get the same answer. I promise you this is the right answer. Okay, so that is 2.7, solving inequalities, but also looking really heavily into the idea of interval notation.